right. Hi, everybody. I'm Sarah, and I'm going to start by reminding those of us who haven't been paying attention to the social sciences lately that web data is revolutionizing social science, giving them access to vast new stores of data that are letting them answer a lot of exciting new questions. And what we're going to be talking about today is using programming by demonstration to democratize access to that web data. So I did a formative study looking at the kinds of data sets that social scientists and data scientists are trying to reach on the web. And then I went back and designed and implemented a tool that can actually handle those real-world use cases. So the end result is a PBD tool that real users, real social scientists are using for real tasks right now. And let's start with a quick reminder of just the scale of the data that's out there. There's so much content. So 10 years ago, Google was indexing 1 trillion pages. Now it's past 60 trillion. So there's so much content, and it's constantly growing. A quick question for folks in the audience. Have any of you actually written a web scraper? Yeah, so it looks like there's a lot of us out there who realize that there is value in collecting web data. And of course, y'all have the skills to do the traditional programming that you would use to write a web scraper. But increasingly, we're seeing that non-programmers are also getting interested in access to that data. So for social scientists, a lot of it is about the fact that there's user-generated content. And so you can study humans by using that. Or it could be about the fact that stuff that used to be only available via censuses and interviews and surveys is now suddenly actually uploaded to the web, and they can get access to that. Or sometimes it's just about the fact that it's really hard and tedious to actually manually collect data, and it's easier to automate it. So I'm going to run through a quick example here. This is some really fun and interesting data that folks collected about gender, race, age, and film industry. I pulled out a couple of fun insights that they found about gender and speaking roles and how that varies based on who's writing and directing the movies. Now, they collected this information manually, and that was reasonable because it was 100 films, so that was a reasonable scale. But if you actually look at this IMDb data, you can see that IMDb knows about 11,000 films from that year. And if they wanted to scale up to 11,000 films, doing it manually is not really going to cut it. Wouldn't it be nice if instead we could actually automatically collect this data? So what does it look like when we actually automate data collection on the web? Here are some libraries. Some of them might be familiar to you folks. So Selenium, Scrapey, Beautiful Soup. The key thing that binds all of these together is that in order to use them, you really have to be able to reverse engineer the target web page. That was fine back in the day when you sort of loaded your URL and you got back your DOM, but now pages are extremely interactive. So you also have to be able to reverse engineer the JavaScript that's running on the page. You have to reverse engineer how it's actually communicating to the server right now. All of that is not really in range for the sorts of users that we're talking about. So we did a survey, we did a formative study asking what kinds of web data these folks wanted. The first thing we heard was that they're not just extracting data from one page. So there are tools out there for doing that, but that's not what they're seeking. They're looking for data where it's all spread out across a whole range of hundreds, thousands, even more web pages. And the way that they're getting the data is, they're following clicks, they're using forms, they're doing pull-down menus, they're submitting forms, they're interacting with a bunch of autocomplete widgets and all the same stuff that you're doing when you're navigating the web. So in the example of our movie data, that's multi-page because they're starting at the list of movies, and then they go to the movie detail page. That gives them a list of actors, and they have a different page for each of the movies, that kind of deal. But even more critically, they want hierarchical data. So we have to be able to traverse and ultimately produce tree-structured data. So in the case of the movies, that means we're not just getting a big table of movies. We want to go through movies, and then for each of those, go through all of their actors. So we also asked what kinds of tools are accessible to them. So traditional programming was not really accessible for all the reasons that we already discussed. We talked to one team that had actually had someone who wrote a scraper in the past. So all of them had basic programming skills. There was at least one person on the team who had written, say, a data analysis script. But there was only one team that actually had written a scraping script in the past. They had written it for a very standard, old-school, static page. The current data set that they were trying to collect right now was, a very Ajax-centric site, and they tried, and eventually they just threw up their hands. They said, this is not in range, and so they gave up. Manual collection, to our surprise, this actually was considered a very reasonable way. This was the only tool that folks were actually using right now. So one team had just hired a high school intern and said, okay, your job is to sit in front of this browser, copy data into Excel. And that was literally what that person did as their job. And then there was another team that wanted a really large-scale data set, but they said, okay, well, let's just get a sample, and they scaled it back, and so they had sort of a smaller version that someone sat down and collected once a week. So this is sort of a mixed bag, because on the one hand, they have the skills, and this was the thing that was actually happening in practice. But of course, it's not very satisfying, right? It was slow, it was tedious, and it was forcing them to use small-scale data. So they used it, but they didn't especially like it. Programming by demonstration. Now, there are some tools out there that you use programming by demonstration to help folks do data collection on the web. It's an attractive domain because browser use is the primary skill that you need. Unfortunately, it turns out that the existing PBD tools cannot collect the distributed and hierarchical data sets that they want. So those tools just weren't powerful enough for their use cases. So that was a no on PBD as well. Let's quickly refresh on what programming by demonstration actually is. So it's closely related to programming by example, for those of you who know that. The idea is the user gives us input-output examples, and we use all of that to then synthesize a program. With programming by demonstration, we actually get even a little more data. So we get to watch the user taking some actions to transform the input into the output, and then based on all of those demonstrations, we will go ahead and produce the program. So I have been working on helping non-coders and especially social scientists to collect web data for a number of years now. This is part of an ongoing project, and I've been doing a lot of different angles on this. So there's some web research in there, some language design research, some systems research recently. But we're going to ignore all of that today and just focus on this user interaction, on going from the user demonstration to the program, and in particular on the form of the demonstration that we want from the user. So we know that users want hierarchical data, which means they're going to be interacting with multiple tables, but they really like to have tabular data as their output that they're going to manipulate and that they're going to analyze. And so what we have them focus on and what we're ultimately going to produce as output is the join of the various tables in that hierarchy. So basically what we want them to produce as their demonstration is how to collect the first row of that join data. So each of the tables, one row from each of the tables in sequence. So for our IMDb case, the user is going to load up a URL. That gives them the list of movies. They'll collect information about that first movie. They'll go ahead and click over to the details page. They'll see the list of actors, and they'll collect information about the first actor in the first movie. That's all the information that we're going to collect from the user. Now, that's not a lot of information, so you should be asking yourselves, can we even offer this interaction model? Is that reasonable? And there are several key technical challenges here. So in particular, the fact that we really need to handle hierarchical data means we need nested loops. And that is a long-standing open problem in program synthesis, so that one's going to be tough. Relation ambiguity, we're asking them to produce only one row from each of the tables that they're interacting with. Now, that's not going to give us a lot of information on how to pick which relation they want from a given web page. There's also the question of readability. So in order to make these scripts really robust and make them handle modern web pages, you have to run these very low-level events, but the user doesn't want to see that. Even a programmer doesn't want to see that. It's kind of gross. So problem one, hierarchical data. Why do we need these nested loops for hierarchical data? So here's our movies actors example. You want to loop over movies, and then for each movie, you want to loop over actors. That's why we need these nested loops. But like I said, it's an open problem, and I'll tell you why. So basically, if you look at that little square in there, that's the programs with no loops, right? That's not so many programs. We can consider that space and probably find one that's going to work for us. If all of a sudden we're allowed to consider loops, then there's a much larger space of programs, lots more programs to consider. And if we allow as many nested loops as we want, well, now it's a huge program space. And so this is why often if you'll attend program synthesis talks, one of the questions you'll hear at the end is, does this produce programs with loops? And usually the answer is no. And every now and then the answer is, actually, we have single-level loops, and then everyone's really impressed. But if we want to handle nested loops, this is just such a huge space of programs. And if we have this very ambiguous demonstration from the user that didn't give us a lot of information, how are we going to pick from among all of those different programs that are allowable now? Past solutions in web automation, programming by demonstration tools in the past have not tackled hierarchical data. And so we really don't have that information for this domain. On the other hand, there are other domains that have tackled nested loops. So SmartEdit actually did some nested loops. The way they had users do it was they had them manually mark this is where the loop begins and this is where the loop ends. Now, they did a user study with 6 computer scientists, and of those 6, only one of them was actually able to successfully complete the nested loop interaction. So that's not really going to be feasible for us. It doesn't seem like that's sufficiently error-free for us. So our solution is to design the user interaction to make search tractable. So we're going to enter into a contract with the user. And the contract is, if you perform one iteration of each loop ordered from outer to inner, then we can get you your program. Now, it helps that, of course, the web is designed such that you pretty much always have to interact with the outer loop before the inner loop, so that's going to help us enforce this contract. But basically what's going on is let's start by assuming that we know the relations that are interesting and exciting to the user. So we know about this movie and actor relation. We can go ahead and then label all the actions that the user took during the demonstration based on whether they used one of the cells of those relations. At that point, we can go ahead and add in one loop for each relation, starting before the first use of each cell. So you can see that we add in that movie loop right before the first use of a cell from the movie relation. So basically, the takeaway here is if we want to add loops efficiently, let's first find objects that should be treated together. Now, this is a little wild, right? I said we should first find these objects that should be treated together, but I was just assuming we knew about these relations, which is, of course, how we're getting those objects that should be treated together. Where did we get those? And so that's the next problem, relation ambiguity. How do we figure out what relations are actually relevant here? The user has not given us a lot of information, right? They clicked on this node, they scraped this node, and then this one they were typing into. We have this sort of set of interacted nodes, but we don't have information about the particular relation that they want. So here what we have is they have scraped these two nodes circled in red. If we as humans look at this page, we're probably thinking to ourselves, that title node doesn't really look like it's part of a relation. So let's say maybe that's not in it. Even then, we still have some ambiguity because what do we actually want in the relation based on this first genre? Do we want all of the genres from movie number 1? Do we want the first genre from all of the movies? Maybe we actually want the list of all the genres that appear on the page. That's also totally reasonable. All of those are totally reasonable. So the issue is that there are many different relations that we could extract from any given web page, and we have to decide which one we want. Past solutions. Basically, the past solution in relation extraction, and there are a bunch of works on this, are to have users label multiple rows. And we're happy to have that interaction as a back-off, but we're really dedicated to this single demonstration, single row interaction. So we don't want that to be part of the usual workflow, the common case. Okay, so our solution, I'm not going to dig in on the details, but the key insights here are that we want to actually start by assuming that all of the interacted nodes are part of the relation. If that doesn't work for us, we can back off to smaller and smaller subsets. And then the next thing is we're going to take advantage of the fact that a lot of web pages are actually generated from templates. So let's run through this concrete example here. We will start by assuming that both of those nodes are in the relation. Now when we try to find if there's any other segment of the page that was generated with the same template, we're not going to find anything. It doesn't look like anything else was generated that includes both of those two elements. Now, on the other hand, if we try with the smaller subset of just the action node that you see highlighted in orange, this time we're going to say, oh, actually, this other thing that's next to it highlighted in purple, that looks like that was generated by the same template. And so when we pass those off to a relation extractor, we'll get these nodes highlighted in green, which looks like a pretty reasonable relation. And so basically the key idea here is you want to take advantage of domain-specific patterns. So in this case, we were able to take advantage of the fact that there are some best principles for how you actually design web pages, in particular that logically related information should be presented in similar ways over the course of the web page. And we can use that to find objects that should be treated together. I'm going to briefly talk about readability. So those of you who have done a lot of web stuff know that the page is allowed to react to any DOM event. That means that in order for us to actually be robust, we need to run all of those same low-level DOM events that the user might raise when they're interacting with a web page. Unfortunately, this is not very fun to look at, even for a programmer, and definitely not for a non-programmer. Past solutions, this is actually a new problem. So when the prior web PBD work was being done, the web was much less interactive, and so they basically just didn't work on AJAX pages. They didn't have to tackle that. So our solution is reverse compilation. We still need to run all those low-level events, but we don't have to show it to the user. So let's just compile and reverse to this higher-level language, Helena, that I designed, and we will show that to users so that they can still get some idea of what the program is doing. They can still understand what's happening without having to look at the low-level ugliness. And so the takeaway here is that it's okay to have your low-level program at one level and then have the program that you show to the user be at another higher level. So let's scrape some stuff. We're not going to do the live demo because my Wi-Fi was a little patchy this morning and web scraping requires the web. So we've opened our Chrome extension. We are going to grab some information about that first movie. Now we've opened the details page for the movie. We will go ahead and grab some information about the first actor in the first movie. You can see the first row off to the left. Now we have provided the entire demonstration. That was all we had to provide as the input to the tool. It is looking at the web pages with which we interacted, and it's saying they interacted with the first movie. Maybe they want to interact with all movies. It's going to do the exact same thing for actors. Now we'll run the script. What we'll see on the left is a preview of the data set that it's actually creating. Off on the right, we will see the browser window that's actually being controlled to get access to all of that data. And so you can see it's gotten the first 15 actors from that first movie, and it's doing the same thing for movie number 2. I'm sorry we don't have the live demo. If you want to see the live demo, come find me. We can run it on my laptop. We can, for that matter, run it on your laptop. Come and talk to me about that. So we did a user study. Obviously, the ideal would have been to actually compare going from knowing nothing about scraping to being able to use a PBD tool, and compare knowing nothing about PBD scraping to all the way using traditional scraping. Unfortunately, that's a lot of skills to expect someone to pick up in the course of a 2-hour user study, and so we don't actually do that comparison that we'd really like to do. What we do instead is find coders who know all the skills right up until the particular scraping library, and then just have them learn the particular scraping library, because we're really interested in the learnability. So the user study here, within subject study, 15 CS PhD students. Each of them was assigned one of 2 tasks, and they are going to do it with 2 different tools, Helena or Selenium. Selenium is a traditional web scraping library. 9 out of the 15 had prior scraping experience. 4 out of the 15 had actually used Selenium itself before. So those folks weren't even using, they weren't even learning a new library. They were just learning the particular scraping task at hand. So the context here, we're interested in comparing PBD to traditional scraping, traditional programming, not just in the context of web, although obviously we are very interested in that, but also just more broadly. There are not a lot of head-to-head comparisons of these strategies. Most of the ones that have happened so far, they've shown really great speed-ups, but really only on small tasks. The best we've seen in the literature, it was about 12 minutes of save time. So we're really interested in whether we can use programming by demonstration to handle real programming tasks, large programming tasks, really save programmers some time. And so that's one of the things we wanted to look at here. So can users learn PBD faster? Turns out the answer is yes. So you can see these purple bars, that's people going from not knowing Helena at all to having written the program that solves the task in about 6 or 7 minutes. The orange bars, that's folks using Selenium. Basically, most of them timed out at about an hour, so we had them all cut off at an hour. The completion rate with Helena is 100%. With Selenium, not as good. And what we're seeing is that we really are getting those large magnitude, huge time savings that we were hoping to see. So this is a real programming task that would take a real programmer, an hour, some amount of time. And so we're saving 47 minutes, 52 minutes. That's a lower bound because, of course, probably some of those folks would have actually taken more than an hour to finish. These ones that I've highlighted in red, those are the folks who actually already knew Selenium, so they weren't even learning the new library. They were just learning the particular task. We wanted to know if users perceive PBD as more usable, also if they perceive it as more learnable. Yes. We also wanted to ask what tools folks would want to use for future scraping tasks if they faced a task in future. All but one said that they would be very interested in using Helena, so that was encouraging. We got some really fun qualitative results. I'm not going to dig in too deep, but some of the common threads were that people really liked, after dealing with Selenium and the pain of doing the loops in there, they liked not having to deal with the loops themselves and having that automatically inferred. Also, folks said it felt like magic. It just worked like magic, so that's always encouraging to hear. But of course, that's not the real test, right? Those are computer scientists. What we really want to know is, can folks who are social scientists and data scientists use this for real tasks? And the answer is a resounding yes. So we have 15 to 20 collaborations, depending on how you count folks who basically came back with new permutations of their teams to tackle new projects after an original project. This team of sociologists, and they've actually lately been joined by some real estate folks, we've had a really close collaboration with them. They started with that question that you see up there, but they have since expanded their mandate. At this point, they have written 6 different scrapers. They have used an end-user parallelization language construct that I implemented to actually parallelize these, and they run them around the clock. So this is being used for real tasks. Quick summary of contributions. Basically, it's a demonstration model that people seem to really like. Also, a solution for the key technical challenges that are involved in actually providing that demonstration model. So handling hierarchical data, dealing with relation ambiguity, and then making sure that the output programs are readable so that folks understand what they're running. That URL on the left, if you go to that, you can actually get this tool from the Chrome store. We have just put it on the Chrome store. We're excited about that. And it's all as a Chrome extension. And you can also, of course, get it through the GitHub in the traditional way. And with that, I would love to take any questions.
Questions? We have time for, I think, one question. Go ahead, Nicole.
Hi, I'm Nicole Sotanum, University of Toronto. I was wondering whether you had any considerations on like the contextual and ethical factors of scraping. Probably not the scope, but then again, just curious whether whether you considered intervals in between requests, which is considered the polite thing to do when you're scraping. And the second question is, what about websites that do not allow for scraping, or websites in which like the rules for scraping are somewhat gray or undefined? Do you do any sort of control or like oversight over these cases?
Great questions. So in terms of the making sure that we're not overloading servers, that is something that, as in traditional scraping libraries, the user has control over. So I didn't show you what it actually looks like when they edit that sort of blocks-based programming language representation of the program that comes out. They can pull in weights and make sure that they're not overloading. We do not do that automatically. The speed is somewhat slower than a lot of the traditional scrapers, just because we make sure that we're running all those same low-level DOM events that the user runs in order to get robustness, as that keeps the speed a little lower. Whether or not that's a good thing, hard to say. On the question of whether we're looking at, sites that allow scraping or not, so basically we treat this as a tool that people would use in the same way that they would treat a typical scraping library, right? So we're not making anything possible that wasn't possible before. We're just making it accessible to non-programmers instead of only to programmers. So in the same way that a programmer could use a scraping library to do scraping that they probably should not do, a non-programmer could use this tool to do that. So we would love to, if you have ideas on how we can, be really conscientious about this, I would love to chat with you about that.
I don't. But thanks for your answer.
All right, I know there were other questions, but unfortunately we're running a little behind on time, so come see Sarah afterwards.